Good afternoon. Can everybody hear me and see the PowerPoint slide?
Yes.
Okay. Any questions?
Yes, Professor, I had a question on question 3 of exam 1. I'm going to pull it up. So question 3 says, oh no, I pulled up the exercise set. Sorry, but it was the one where you have to make an FA and then a DFA and then reduce the DFA.
Correct. So which there were two.
Yeah, so let me see on exam 1. So it says construct an NFA for each of the following regular expressions, then find the corresponding DFA, then reduce the DFA, and it gives A, like the first expression is parentheses A squared.
I have it. I'm just asking which do you want me? What is your question about which one?
Oh, would you mind going over B on 3 on exam 1?
Okay. I guess this is the question. And so here we are. Yes, this lecture is all questions. If you have no questions and you're not interested in my answers to somebody else's question, this is a waste of time. I hope it isn't. All right, so this is the alphabet, and we are interested in the result for that. So you do first a DFA for 0, 0, and then a DFA for 0, 1. Then you star these, then you take the union, and then you do another question. Another automaton for the second 0, 0. This, of course, is a different automaton, and a second automaton for 0, 1. So this is again a different one. So if we go just cutting through, you're going to get 0, 1, 2 for 0, 0. You go to 1 and 2 and 1, and so this would be 0, 0 star. And then we do 0, 1 star, which is 0, 3, 4. If we do it systematically, so we go from state 0 under 0 to 3, from 3 under 1 to 4, and then 3. And so this is 0, 1 star. And then you take the union. How much detail do you want to see?
The entire problem.
All right. So then we have 0. Why is this not working? reason this thing is not willing to work. Come on. I can't write anymore. For whatever reason, it refuses to accept that. What do I do?
Maybe the easiest solution would be to close the PowerPoint and then make a new one.
Well, I have a number of them, but none of them work. You want me, all right, I can just close the whole thing. Nope. Come on, this is ridiculous. Well, what is draw with touch on? What does that mean?
I think that means that's the normal mode that you've been doing.
Well, that's what I thought, but draw with touch, that's what I have. All right. Stroke erase.
Input from your touchpad or whatever you're using.
I'm using a stylus. That's what I'm using. And I seem to be able to do something with my fingernails, but I can't do anything with the stylus, which is completely ridiculous.
Sometimes the styluses are like their own devices, right? Like maybe they have that it ran out of battery or something.
Well, no, this one doesn't have a battery. Oh, come on. That's what I need.
Well, can you try like opening a different application and seeing that it's not just PowerPoint? Maybe like Microsoft Paint?
I have no idea that this is all I have. Come on. This is ridiculous. The mouse now allows me to do things, but the stylus doesn't. So what you get, well, it will be very painful, but
Sorry.
using that bloody mouse. So you get the union of this one and that one, which is 1, 3, and nothing, and then 1 is 2, and nothing, and 2 is 1, 3. I'm sorry, we do the union, so this is 1, and then this is nothing, and then 3 is nothing, 4. and 4 is 3. And nothing, and then you have 1, 0, 1, 0, 1. So that is now the union. This is that first parenthesis. Then you do the second union, which is basically 0, 5, practically no control. 0, 5, 6, 7. 0, 1, and so you do 0, 0, and 0, 1. So 0 goes to 5, and 5 goes to 6, and then I need 8, and 5 also goes to 7, and 7 goes to 8, and 1. And then 6 goes nowhere, and 7 under 0, and then 7, 8, and so you have 1, we have 0, 0, 1, 0, 1, and then you change that into a 1, and you have 5, 7 here, and 5, 7 here. And so this is now the 0, 0, 0, 1, and then you just have to do the concatenation. Look, I'm unable to do that.
Okay. Yeah, it's all right. I'll review the.
Let's see. Try disable draw with touch, and then I didn't read. Well, you see, the pen doesn't even allow me to do that.
Yeah, maybe someone can ask a question that doesn't require so much drawing, and then I'll review the lecture before the first exam about this topic.
I have no idea what's going on here. Obviously, I got to some point, but I didn't. So let's just kill that stupid PowerPoint and see. Don't save and open it up again. And blank presentation. And it is still not working. Come on, this is completely ludicrous. either. Well, this is a stylus. It has very little to do with any electricity. See, I can scribble with my fingernail, but I can't use the stupid stylus. Okay, I have to share my screen. Sorry about that. I forgot about that. So there we go. But it doesn't help you. See, I'm writing vigorously and nothing happens.
On the top left-hand corner, it seems like you have draw with touch on.
Yes. Well, what if
Can you take that off? Now it looks off. Try drawing.
Yeah, nothing works.
Weird. I don't know.
Yeah, well, that's exactly the problem that we have. I cannot figure out what on earth is going on here with I mean, as you can see, when I prepared the slide just 5 minutes ago, it still was working and now it quit. Well, let me try to give answers that don't require writing or minimal writing because obviously I can.
Professor, is it possible to use like something like Excel where you could just type into cells? Maybe that might also make it possible.
Most of the stuff can't be done with typing that easily. That's why I'm using a pen. I mean, to type these stuff in, you need a formula editor, which I'm not having installed for this. I can draw little things. Go ahead and ask questions, and I will see to what extent I can give you answers. Any questions?
I have a quick question. I'm sorry, I had to step out for some office hours that were going on at the same time. So are we, is there an issue with the writing?
Yes, I can.
Okay.
Can. The stylus doesn't do anything.
I'll phrase my question to not have to do that then. So I have my question is about a problem on exam 3. So we just got the grades back. I looked at, the problem and I see that, the mistakes that I made. And I guess I was sort of wondering, I guess if we could just talk about how to do number 3, I think it was, where, let me pull it up. Okay. Right, we're to construct a PDA that accepts by empty stack for a given language.
Yep.
So basically so the given language basically is already not in Chomsky normal form, right?
Right, but it is very easily converted into Chomsky normal form.
Right, okay, I think I got that part.
I mean,
and then it's fairly easily converted into Greibach normal form too, right?
I'm sorry. It has nothing to do with Chomsky normal form. It is strictly Greibach normal form. I mean, you're absolutely right. It is not in Chomsky normal form, but Chomsky normal form is entirely irrelevant here.
Oh, I thought that was typically
no.
It's not. Okay.
I never suggested, and in fact, I remember somebody had a similar question, and I very clearly stated Greibach normal form and Chomsky normal form are entirely independent.
Okay.
So if you have a Chomsky normal form, then that is a particular form. So Chomsky normal form is basically where you have a variable and it goes to either two variables or it goes to a single terminal. That's Chomsky normal form. Rybak normal form is where you have a variable where you have a terminal and then you have a bunch of variables, a zero or more. So m is greater or equal to 0. So if you want to get Chomsky normal form, you go through the process that I described in class. You simply use that zipper idea. You convert all the right-hand sides into variables. If there are terminals, you get rid of them by having a variable. Say if you have a terminal little a on the right-hand side, then you just replace that terminal little a by x sub a, and you add a production. X sub a goes to a. We've talked about that extensively, and so you're going to get productions where the right-hand side consists only of variables. Now, the only time you don't do that if you have only a terminal that you leave, because it is already in that form. And then, so if you have a variable go to a sequence of variables now, using this trick, we can get rid of all the terminals on the right-hand side. So this thing here then is two or more variables, and this is where the elimination of unit productions comes in, because otherwise you might have A goes to B, which would be not, you couldn't deal with that. But once you've eliminated unit productions, then you have at least either a single terminal or you have at least two variables after you did all that. This, of course, assumes you don't have any epsilon productions, which is what you have to do first, eliminate epsilon productions, and then the unit productions. And then you use that idea of the zipper, that you split up the first terminal, and then you get A goes to that first terminal, I'm sorry, first variable, and then you do A1, and then A1 then generates one after the other until you have all of them. The only time when you get both of them is the last two. And so in that way, you're guaranteed to get the required format for all the productions. That is completely independent and has absolutely nothing to do with Greibach normal form. Greibach normal form basically is this format: a terminal followed by zero or more variables. And that is achieved by using the construction we discussed in class. The primary issue here is elimination of left recursion, which means you are going to number your variables. You fix an order, and then you ensure that each of the productions for the AI variable starts with something that comes after the I, so that J has to be strictly greater than I. And then, of course, there's stuff afterwards, but that's not really important. You just have to write it down. But the crucial issue is that after you've done the elimination of left recursion, you now have a situation where every production satisfies this, that if you have an AI production, whatever I is, that the right-hand side of that production cannot start with any variable that is higher up in this listing. It has to be strictly lower. So if there is I here, then the J has to be below that I. So it's underneath. And that then eliminates all left recursion. So if all of the productions are of this type, then you have no left recursion. No left recursion. And that means then by back substituting, it means in particular, of course, that the last variable must always, the right-hand side must always start with a terminal. And then you can back substitute that into what happens before. So you do the an minus 1. It can start either with a terminal, which is fine, or it can start with an, and by substituting the an productions for that leading an, you then get an minus 1 productions that all start with terminals, and so on and so forth. So in that way, you then get Greibach normal form, but this is completely independent of Chomsky normal form. The only thing that is in common is no useless symbols, useless symbols have to be eliminated, epsilon productions have to be eliminated, and unit productions have to be eliminated in both cases. But other than that, the processes are completely different and independent. In Chomsky normal form, basically you do that zipper that allows you to sort of develop a longer string of a longer sequence of variables, splitting it up into two variables at a time, where the first variable is one that is up here, and the second variable then allows you to produce the next step, the zipper, next zipper, and so on and so forth. Whereas in Greibach normal form, it's completely different. You basically do the elimination of left recursion. That is the key observation of that. Does that clarify it?
Yeah, well, I mean, that helps. I understand that they're different. So just to, clarify this for me, since if we have encountered, right, so really quickly, for example, on exam 2, we were asked to construct a Greibach normal form for a grammar that was already in Chomsky normal form. Is it an improper strategy, so to speak, to try to go to Chomsky normal form first, or you should you not?
I think that would be a very foolish thing.
Okay.
I mean, this is sort of like saying, uh, I want to go to Galveston, and so in order to get to Galveston, you first go to El Paso, and then from El Paso you go to Galveston. Yeah, you can do that, but it probably is not very good.
Okay, thank you. I understand.
They're completely independent. You claim that you say that they were. I'm now a little puzzled. Did I actually give you in exam 2?
So you didn't ask us to explicitly do that, right? You didn't ask us to convert it to
Exam
Chomsky.
2, when you were asked to.
It was just already given in Chomsky normal form, so I was just
Yeah, it happens.
making sure.
But this is entirely coincidental.
Right, I understand.
Basically could have, instead of saying S goes to AA, I could have said S goes to AAA. That simply means you would have had to write a little bit more. So I kept it at a minimum. Unfortunately, you misinterpreted that and thought you had to go first to Chomsky normal form, which of course is not really true at all. Sorry about that.
I should have known better. Thank you, though.
Any other question that I can answer without having to write an awful lot?
Can you go over the next question from that same test?
Okay. Exam 2, question 4? No, which question?
Actually, I'm referring to exam 3, question 4.
All right. Exam 3, question 4. Well, that's the construction that I gave you. You simply have to do that pattern matching exercise. That is clearly not something that I can do without a stylus.
Okay.
Basically, let me see what this amounts to. Hold on. I feel so inept with this. This one. No. Wasn't this one. I'm trying to find the PowerPoint that described that. Yeah. Okay, let me share that with you. This one. If you recall, where are we? All right, can everybody see this given a PDAP?
Yes, we can see this, Professor.
Yes.
This is where you have to do the pattern matching. And so you basically have to make the correspondence So this Q1 is that Q1, and that Q is this Q. These are probably the only ones that can be a little confusing because it's Q and Q subscript and so on. But so this Q1 is this Q is that, and then you have Q2, Q3 through Qm plus 1, where the Qm plus 1 is basically this. And you just have to do the pattern matching as I have indicated here, and that's I mean, the example that you did for exam 3 is really very, very similar to these questions. And obviously I can't write that without my stylus, which is completely useless nonsense. I'm very sorry about that, but this does not look like anything I can fix. So that's basically what it boils down to. This is what you have to apply, and then you have to do that pattern matching. So you take essentially an entry. So if you look at this, there is this inside, and so this is delta of Q0, 0, and Z. And so what you do is you have, this is the delta Q little a and capital A, and then that is what's sitting there. So this is that. And then you just have to do that pattern matching. Does that sort of help you? I guess it doesn't. I don't hear anything.
I'm not sure if anyone else has a question, but I wanted to just, I guess, discuss the differences between recursive and recursively enumerable, since I've still been having some trouble kind of grasping these concepts.
Absolutely. Okay, go right ahead.
So I guess, I mean, I've been reading my notes, and I guess I just want to start from the ground up, getting all my confusions out of the way. So when we define a recursive language, that means that we can, a Turing machine can, if it can halt for every input that is accepted in L, then that means the Turing machine can effectively only provide a yes answer if the input is in L. Does that make sense?
No. If you have, you started out by saying you have a recursive language. Okay? Now, if you have a recursive language, you're basically already prejudging things.
Okay.
In that a recursive language, I'm looking for the corresponding slide that we had. Hold on, must be.
Yeah, they were from the 26th, if that helps.
26. Okay, then let's go there. Okay, let me share that. Okay. Do you see undecidability?
Yes, I do.
Okay. So this is the definition. A language is recursive if there exists a Turing machine that halts for every input and accepts L. So it basically requires you to have a Turing machine that will always halt. That is a recursive language. Now, that doesn't necessarily mean that every Turing machine for that language will halt. All it says is that there exists a Turing machine that will, for that language, that will halt. Now, as I said, then the next thing is recursively enumerable, which is, of course, more general than recursive, because it basically says there exists a Turing machine that accepts every word in L and does not accept any word not in L. So this sounds like a roundabout way, but it does avoid the issue of what happens if the word is not in the language. Okay? It basically says if the word is not in the language, the word is not going to be accepted. But it doesn't say that that Turing machine is going to halt. It will have to halt if the word is in the language, because it can only accept by it, when it accepts, it halts. But if there's a word not in the language, then there is no statement made about whether the Turing machine halts. And so in this particular case, we can immediately, if we can construct a Turing machine that accepts every word in a language and does not accept anything else, then we have, by definition, established that this language is recursively enumerable. So this is a more general or weaker kind of statement than that the language is recursive, because in order to show that the language is recursive, we actually have to establish that there exists a Turing machine for that language that will halt on every input. Does that clarify something?
That clarifies a little bit more than before, because I had been reading my notes and I thought I had just written it down confusingly, because so basically for the condition, or sorry, the situation, if a language L is recursive, then the Turing machine will halt for every input, but it also just happens to accept that language.
Right. I mean, basically, I am, because I want to be very clear, I have to add that it accepts L. That this, of course, usually goes without saying, but I am emphasizing that because it is obviously important. But that tends to fall by the wayside. Obviously, if we have a language L and we have a Turing machine for it, it is sort of tacitly understood that it will accept that language, which basically means it accepts every word in L and nothing else. And if that Turing machine halts for every input, then that establishes that the language L is recursive. If we don't know whether the Turing machine halts on every input, but we do know that it accepts precisely those words in the language L, then we simply have established that the language is recursively enumerable. This sort of is what we typically do. I think most of us probably don't particularly spend an awful lot of time when we write down a Turing machine to verify that in fact it halts on every input. We're sort of focusing on the issue, how can we make sure that this Turing machine will actually accept precisely those words that are in the language, and we're not really that obsessive about showing whether it halts on even the screwiest input. But of course, that is exactly what is necessary in order to be able to say that the language is recursive. So if we just construct a Turing machine that accepts every word in L and does not accept any word not in L, then effectively we've established that this is a recursively enumerable language. And if we want to go beyond that, we would actually have to show that that Turing machine halts on every input. Does that sort of
Yeah,
make it?
I understand the difference now. I understand the difference. It was like in the back of my mind, but it makes sense now. A lot better.
Well, it does make sense, but it is tricky. So that's why I'm certainly happy to try to elucidate this as much as I can. But because it is a tricky kind of question, we keep between the recursive and the recursively enumerable. So in essence, recursively enumerable is the more general kind of thing. Every language that is recursive is also recursively enumerable, but not every recursively enumerable language is recursive. Okay? Did I now confuse everybody? If you take a set diagram, then this is RE, and a subset of that is recursive. Obviously, every recursive language is recursively enumerable, but not every recursively enumerable language is recursive. And if you recall the language that we define L sub U, this is precisely a language that is sitting out here in this diagram that is recursively enumerable, but not recursive. We showed that it is not recursive because its complement is not RE, so there is not RE. And if you recall that, LD, we showed that LD is not RE, and that LU complement is effectively LD. And so, since LD is not RE, and LU is recursively enumerable, it follows that it cannot be recursive. Because if LU were recursive, then its complement would also have to be recursive. But since LD is not RE, the only way that these requirements can be satisfied is if LU is recursively enumerable, but not recursive. So that essentially was the program that we dealt with last week, both lectures, namely that you, in fact, have languages that are recursively enumerable, but not recursive. And I guess this is what we did. Yeah, recursive is a subset of recursively enumerable. And so we had this case RE but not recursive, then L complement is not RE. And of course, it wasn't clear that such a language exists. And that was, of course, what we did on Tuesday last week, to actually show that LU is recursively enumerable but not recursive. So we basically did this diagram. LD is not RE, LU is RE but not recursive. Any other questions? Question 5 on exam 3. Okay, you want Turing machine. Basically, let me get to that. So we're going to share this. Okay, so if this J here were an I, so if we had AI, BI, and AI, then it would be almost exactly the Turing machine that I described in class. I had A, B, and C, but of course the second, whether you have A's or C's, doesn't make a whole lot of difference. In fact, if you really want to reduce it to the question that you know already how to solve, you first change this language into A to the I, B to the I, C to the J, which you can, of course, very easily do by simply going through the input, and after you've changed from A to B, then when you change from B to A, you just change every A to C until you hit the blank. So this is one pass that gets you through A, and then B's, and then you put in C's here instead of, and so there's your blank. And so you can do that in one pass with a change of state here and a change of state here, where the first A is going to be changed into C, and then all the other A's are going to be changed into C. So that'll get you to this language. And then basically what this language does is almost exactly the same thing that we did in class, and this is exactly what we did in class, where the same number of A's, B's, and C's. And in this particular case, of course, since J is greater or equal to I, once you've matched up the A with the B and with the C, and then the next A with the next B and the next C, and so on, until you get to the last A, the last B, and the last C. And now this is, of course, where things work with this, which is a little different from that. Once you've matched that last A with that last B, and then you match it to a C, then there could be another C or 2 or 3 or 4. There don't have to be, because J is greater or equal to I. So if J is equal to I, then after that last match, the last A being matched to the last B, being matched to the last C, the next thing could be a blank, or it could be a C, and so on. And you keep on passing by any C's that you see until you hit a blank, and at that point you accept. Does that clarify? Okay. Any other questions?
Really quickly about exam 3. I don't know if you still have it up. This is sort of a, I don't know, kind of a pointless question, because I guess I didn't lose a ton of points, so I assumed right. But on number 2 on exam 3,
questions are pointless.
so on number 2 on exam 3, the language given is, I read that as 1 followed by 0 to the 3i. That's the correct way to read that, right? Not correct. 10 to the 3i, right?
No.
Okay, I just wanted to make sure. You had never done that to us before, so I just wanted to make sure that I was reading it right.
Yeah, I mean, obviously, we talked explicitly about that. Exponentiation in this case binds, of course, stronger than concatenation, which is, if you had something like, okay, if I had written 1, 0 star, then obviously that star would be only applicable to that 0. This is not 10 starred. If I wanted 10 starred, which of course I did, I have to write that. And so if I say 1 to the I, 1, 0 to the I, then that is very different from 1, 0 to the I. And whether this is now I or 3I doesn't make any difference. Okay? Does that clarify it?
Yes, definitely. I had it, implicitly understood. I just wanted to make, triple sure.
Absolutely. Triple. In this case, 3I, right? Any other questions? Any other questions? Any other questions? Well, I hope you got something out of this course. This is probably the most theoretically oriented computer science course that you encounter unless you really go into theoretical computer science, but most of you probably stay away from that as far as you can. But it is important to understand that we are looking at kind of thing where we have recursive languages, where we have regular languages, be careful, regu. So this is a class of languages, that is the smallest. Then we have context-free languages. And then we have recursive languages. And then we have RE languages. But all of these are, of course, very, very few compared with all languages. If you recall, the set of all languages is significantly larger than any of the languages that can be described, because we've demonstrated that the set of all languages is uncountable. So this is uncountable. Recursively enumerable languages are, of course, countable, because every Turing machine has a description. We looked at that. We talked about the encoding of a Turing machine. So any Turing machine is essentially representable using a binary string. And so any Turing machine will be representable that way. So if we enumerate all binary strings, we effectively enumerate all Turing machine descriptions. And so that shows immediately that this is countable. So the set of all recursively enumerable languages is obviously countable because the set of all Turing machines is countable. And that, of course, then still has one more wrinkle in it, because two different Turing machines could, of course, be used to define the same language. So yet still, because we can enumerate all strings, we can enumerate all Turing machines, and therefore we can enumerate all languages that are accepted by Turing machines. So all recursively enumerable languages are countable. And of course, the recursive languages are a subset, and the context-free languages are yet again a subset, and the regular languages are a subset. So all of these things, except for all languages, all of these sets of languages are countable. The only set that is in that diagram that is not countable is the set of all languages. But everything else that we've talked about is, of course, from a set that is countable. And so the ability to actually talk about this in a precise way, and the ability to relate that to what we are interested in, and what I would hope are interested in, is algorithms. Computer science essentially deals with the question, what can we do? What can we solve? And so if we have a language that is known to be recursively enumerable but not recursive, we know we have a fundamental problem, because what we expect to obtain in the context of an algorithm is that that thing terminates with either yay or nay. A recursively enumerable Turing machine, the recursively enumerable language corresponds to a Turing machine that will say yay, but it will not necessarily say nay, because it may not terminate. If you have a recursive language, then of course you have a Turing machine that will say yay or nay, and obviously everything else, context-free languages, irregular languages, and so on, will have that same property as well. But the tricky thing here is that a recursively enumerable language is quite, well, I think you're sort of confused a little bit about the issue of halting, and unfortunately, or fortunately, and depending on how you look at it, it will provide you with additional food for thought, because I would imagine that when you went into this course, it never really occurred to you that there are things languages that could be recursively enumerable, but not recursive. In other words, it is impossible to come up with a device, with a Turing machine, that is guaranteed to halt for every input. And that, of course, to some extent is a little mind-blowing, because no amount of additional work is going to get you to a situation where you can say that this language, say this language that we talked about, L sub u, which is going to be here, recursively enumerable but not recursive, this language is such that you can't get a yay or nay answer. And as we said, the post-correspondence problem is an instance of that. We talked about that, and of course the equivalence problem of context-free grammars. Given two context-free grammars, do they generate the same language? That is another one of those cases where we didn't show that, but I'm telling you that the equivalence problem for context-free grammars is one of those problems that is RE but not recursive. You can easily see that there is a Turing machine for that problem. It will simply enumerate all words in the alphabet, T star, every single word, and then determine whether the first grammar generates it, whether the second grammar generates that word, and if they coincide, then it goes on to the next. And so that, of course, if the answer is yes, if they happen to be identical, then that process will never terminate. So this is an instance of what you have here. Now, if you were to ask the question whether L of G1 is different from L of G2, then that's a language that is in here. So that would correspond to the L sub U. So if they're different, then eventually, if they are different, you will encounter a word that is in one of the two languages, but not in the other one, and therefore you have a witness that the two languages are different, and so it will terminate at this point all grammars G1 and G2 that will generate different languages will in fact be determined that way. So this clearly makes it RE, but if that's not the case, if they happen to be generate the same language, then of course it will not terminate. And so the first question, this one, is out here, not RE. And the second question is in here. It is RE but not recursive. And of course that is because these two are complements of each other. So as we've established, if you have a language that is not RE, well, if you have a language that is RE and you look at its complement, if its complement is also RE, then both of them are recursive. If, on the other hand, one of the two languages is RE but not recursive, then the other one is not RE. So that's what this is all about. And so you may say, well, this is completely useless. Well, that's not really true, because if you were to try to solve the equivalence problem for context-free grammars, you could spend an awful lot of time trying to solve that problem. You may say, well, this is a silly question. That's not really true. There was an instance many years ago when a company in what today is known as Silicon Valley, was looking at a problem that they were trying to solve. We're talking about the early 60s, mid-60s. And so they approached a well-known computer scientist by the same name of Seymour Ginsburg, whether he would be willing. They then spent a lot of time and a lot of effort, $500,000 in terms of 1965 dollars. So this is an awful lot more money today. And they didn't get anywhere with the problem. And so they approached him and asked him whether he would be willing to act as a consultant for them. And Seymour Ginsburg was well known for being a very, very good computer scientist, but he was also well known for being abrasive as hell. And so the VP for research and several other high-ranking officials from the company came and asked him whether he would be willing to act as a consultant for them. And so he said, well, what's your problem? So they explained the problem to him, and he looked at them and said, you're all idiots. He told them to their faces, don't you know that this problem is undecidable? So if you think that these are just completely useless theoretical fun and game things, that may not be true. You may, in fact, at some point when you've tried unsuccessfully to solve a problem, try to look at whether you can show that it is undecidable. And if that's the case, then you know that all the time that you've tried to solve it was a complete waste of time and effort. So this is not totally useless. Most of your problems are probably not going to fall into the category of undecidable problem. But if you have the misfortune of getting one of those, it is probably a useful thing to be able to show that something is undecidable. Any questions before we finish? It is 10 to 4, so anything else? All right. In that case,
I have a question, Professor.
sure.
Who do we talk to appeal our grades on the last exam?
You sent me an email.
Okay.
Okay. Anything else?
Do you think you
Yes.
could quickly go over question 3 on exam 3?
Why are you waiting until the very end? It is. Did you just come?
Yes, Professor.
Well, I'm probably. Which question? Question 3, exam 3?
Mm-hmm.
We've talked about that. Better find out what you didn't attend to.
Okay.
All right. Any final comments? All right, then I wish you good luck, and sorry about the technical difficulties. I'll have to find out how I'm going to get a stylus that actually works. It worked all semester, but now it didn't.
Professor, I have
Yes?
a question. For the final exam, on the syllabus, it says it's from 2 to 5. Will you be giving a extended time frame, like how you did with the other 3 exams?
Yeah, probably another half hour or so.
Okay, all right, thank you.
I'll send out an email telling you when you can start downloading and when
Okay.
it is. Yeah, but it is certainly a little longer, probably half an hour longer than the 3 hours.
All right, appreciate
Okay. All right. Good luck.
it. Thank you.
Bye-bye.
Have a good rest of your semester.
Yes, I will try. Thank you.